Hey everyone, it's Kelly, and this is a problem that talks about pressure and uses the ideal gas law. So essentially, you have one gas A mixing with gas B, and what is the final pressure when they're mixed together? That's essentially the problem. But I wrote it, so therefore it's easy for me to interpret. The difficulty is seeing this for the first time and actually figuring it out. So kind of parsing out the language with the interpretation. So I tend to draw pictures, okay? So, and write the numbers associated with each picture. So this first part, this is 25.1 liters of gas A. So we're going to literally, I'm going to just erase these lines real quick. So we have 25.1 liters of A, and it's at 25 degrees Celsius at 759 torr. Okay, it's going to mix with 21.2 liters of B at 25 C, so we're not changing the temperature, but it's a little lower pressure. So that is the first sentence, okay? Really try to interpret the language and maybe draw some pictures and associate the numbers to each picture. That can really help you. Calculate the total pressure. Okay, so this is the question. Calculate the total pressure. So P total is unknown, okay? But they're going to be pumped together, and it's going to have a final tank of 10.4 liter. So that's your volume, and then your temperature is the same. So if you want to know P total, you need to know PA plus PB. So literally, you add together the pressures. But how do you actually figure out the pressures? You need to know the moles of each one, okay? Because that's directly related using ideal gas law. So with that in mind, we can actually do a little math. We have enough information to figure out the moles of each one using ideal gas law. So we have, let me write up here, PV equals nRT, right? Pivnert is how I was told to pronounce it a long time ago. I wonder if they still do that. So we need to know the moles, right? You need to isolate N. But there's a few ways you can do this, really, because I'm comfortable with gas constant in atmospheres. So R is 0.08206 liters atmosphere mole Kelvin. Okay, this is in torr. You can, essentially use the gas constant for torr if you want, but to get a little practice, I'm going to convert to atmospheres. So in general, the pressure that we're given, which is 759, we need to convert to atmospheres. So what is our conversion factor? In 1 atmosphere, there are 760 torr. Okay, so it's practically 1 still, but not exactly. So what is this pressure? This pressure is 0.09, definitely not 0.9, 0.9986 atmospheres. And we would technically round at the 3rd decimal point because it's 759, 3 decimals. Okay, let's see, the temperature has to be in Kelvin. It's the point because the pressure, the gas constant is in Kelvin, okay? So we have 25 C, we're going to add it to 273. So this is 298 Kelvin. Cool. So we have all of the information to actually do the math, right? We can actually, let me change fun colors. We can actually use PV equals nRT and do the math. I like to symbolically isolate the unit I'm trying to figure out. So N would equal PV over RT. I tend to do that before I enter any numbers just because in the long run it is much more organized. So let's fill it in. N equals pressure. So what do we got? 0.9986 atmospheres times volume, 25.1, that's a 0.1 up there, liters. It needs to be in liters because the gas constant is in liters. Units need to cancel. And then on the bottom, what do we got? We got the gas constant, 0.08206 liters atmosphere mole Kelvin times 298 Kelvin. I got, when I did the math, hopefully I was right, I got 1.02507 just for units, or for sig figs, so moles. We would end up rounding at your 1.03 if we stopped, but we're not done yet. That's gas A. There's 1.02 moles in that sample. Plain and simple. Maybe not plain and simple, but there it is. For gas B, we do the same exact thing. I'm going to change colors again because it's fun. We're starting with PV equals nRT, right? Isolate to N, PV over RT. So what do we got for moles? We have the pressure. I'm not going to do the stoichiometry on the side. I'm just going to do it straight in the fraction. So we would do the given pressure, which is 701 torr, divided by 760 torr. Okay, that's essentially what we did over on the left with the 759 torrs. We just divided the two. And then we have our volume is 21.2 liters. We're going to divide it by the gas constant. And then liters atmosphere mole Kelvin. Please don't forget your units. Please, please, please. And then finally, your volume is 298. That is not a 9. 290. I'm having fun with my writing today. The answer I got was going to be smaller than the other one. I got about 0.7946 moles. We would end up rounding at the 795 essentially if we stopped, but we're not done. So our final actual execution of this problem is this bit over here, right? So if we want P total, so P total of the Pivnert, we need N total. Okay, so let's isolate P total. PT equals N total RT over volume. Let's just plug it in, because what can you do here? We can add the moles that we actually calculated. So we have 1.025, I'm just going to stop there for now, plus 0.7946 times your gas constant, 0.08206 liters atmosphere. Oh gosh, let me try that again. 0.08206 liters atmosphere mole Kelvin. We're also multiplying by 298 on the top, and then we're dividing by the volume, which was 10.4 liters. So total pressure I ended up getting to be 4.29 atmospheres. Okay, right? So when you get your total moles, you can figure out your total pressure. So there's an example of interpreting kind of a classic PV equals nRT problem. So hopefully it kind of went through a few of the concepts. Total, partial pressures add up to total pressures. Total moles is directly related to total pressure. Okay, so keep practicing these and hopefully you enjoyed it.